All right, line A4, learning task 8. This is going to be video C, where we're going to go into the full RLC. We've done parallel RL, we've done parallel RC. Now we're going to go into that full RLC. They give us an example here inside of number 4. Now, number 4 is very convenient because we already have got XL and XC that are going to be provided for us. Not that those are hard. You know, at this point, everybody has done a number of 2 pi FL and 1 over top of 2 pi FC calculations to go and establish XL and XC before. This should not be a tripping up point for you, you know, establishing these or not. It's just one less step that we have to go in place. If I take a look at it, once again, I see that I've got voltage that is being supplied, and I can see that I can drop that voltage over top of every single one of my individual components that I'm going to have over there, right? I'll get 120 across here, 120 across here, and 120 that are going to be across here. I also note that my XL and my XC are not the exact same, therefore our circuit cannot be inside of a resonant type of application. So let's go through. They asked for current in each branch. They wanted to know the line current. They want to know the impedance, etc. Currents inside of each branch over here are going to need to be calculated manually because if we go straight to the power triangles off of this, we're going to get the net overall. Now, the net overall is very useful because it does tell us the overall power factor of our circuits that we are going to have and the overall, you know, bars L versus bars C that we are going to have. But to calculate individuals, we still need to go and place this, you know, through with an individual amount of current. So we're going to do that. We're going to say I is equal to E over top of R. Well, we're not going to say that. George Ohm said that. But we're going to go and use this formula over here. 120 volts over top of my resistance. So for the first one over here, it's going to be 120 divided by 20, which we don't need a calculator for that. We should find that we have got a current of 6 amps. Why don't I just make this a hair bigger, or a fair bit bigger. Erase that there, and we will place that in there. So this one is going to be 6 amps over here. This one over here is going to be 120 divided by 16, which gets us to 7.5 amps. Here. And this one's going to be 120 divided by 24. This gets us to 5 amps. Over here. Lovely. We've got our individual currents that are going through there. Now we know that we have got XL and we've got XC. We should remember from earlier studies inside of our theory over here that this current is going to get passed back and forth, and only the net difference later on is going to go and get pulled out of my source over here. In other words, this 5 amps is going to get passed back to here. This is going to pass 5 amps back out, which means that really what we should be seeing is that we should only have 2.5 amps coming in from my source. My source is only going to have to supply a small amount of that inductive amount of current over there. We'll look at that later on once we get to all of our full values off of here. Let's start by converting everything now into power. Same format as what we've done before, E squared over R. You could do V times I, you know, your current and your voltage. You could do I squared R. Any one of those formulas are going to work, but I prefer to work with that one because it is a constant. We're given this 120 volts. We know what's happening over top of each one of those. So the first one is going to be 120 squared over top of 20 ohms. Gets me to a watts value of 720 watts. 720 watts. Then the next one is going to be an XL. It's over top of 16 ohms XL. So we're going to do 20 squared divided by 16, which is now going to go and give me my VARS L, which is going to be 900. Here's where I'm going to follow that convention of my VARS L being going in the upward direction. So 900 VARS L that I'm going to go and have. And the last one that I'm going to go and have is going to be 120 squared divided by my resistive value for this one over here is 24 ohms XC. So divided by 24 gets me to a value of 600. So I'm going to go and have 600 VARS C going down. That's going to be VARS. I'm running out of room here. I always misplan that part. VARS C. So we got 600 bars C going down, 900 bars L going up, 720 watts going across. What we can do now is we can add those all together to go and establish our total amount of VA. So we will take 720 watts, always add in at 0 degrees, plus my 900. They're going to add in at 90 degrees. It's a bars L, plus my 600. They're going to add in at a negative 90 degrees. And all together, this equals a value of 720. It's giving us the XY because that's the format, so we'll just make it display this as a polar. It's giving us a grand total of 780 VA. That's going to be my new triangle going across, so that would be this over here. 780 VA, and it's happening at an angle of 22.6 degrees. 2.6 degrees. Lovely. Now that we've gotten that far, we can go and establish my line current off of this. We can establish my impedance off of this. We can establish my power factor all off of this as well. We're going to jump over to those really quickly. Let's just finish dropping in a couple of these values over here. This one was 720 watts. This one over here was 900 bars L. This one was my 600 bars C over here. Okay, let's go and take a look at this VA, and let's go and take that VA, and we're going to split it out and form our line current now. We've got line voltage, we've got total apparent power, so we can just divide that out of there. 780 at an angle. Oops, sorry. Doing that. We're going to use that one in a minute there, but 780 divided by 120 equals 6.5 amps total. So I've got a total amps of 6.5 amps over here. Now, if you take a look at that 6.5 amps, that 6.5 amps is leaving from my supply, and then it goes over, it hits this junction over here where I'm going to take out 6 amps at angle 0, and I'm going to go and take out an unknown quantity at some other angle based upon what I have over here. I can calculate what that would be by taking this 6.5 amps, and I can go and drop that current into a triangle. We're going to do that, 6.5 amps at angle 22.6. Which gets me to, well, it's still inside of my polar, so we'll do that conversion to XY. Tells me that I've got 6 amps along the x-axis. That's correct, right? If we take a look, I do have 6 amps of resistive over here. And it also tells me that along my y, I've got a positive 2.49, or we're going to round that to 2.5 amps that I'm going to go and have. So in other words, what I get over here is I get a current of 2.5 amps at 90 degrees over here. Does that line up with this over here? We just took a look at this. We said that, look, 5 amps is going to be going back and forth between these two, right? That's going to be the line current that's going to travel through that line. 5 amps to the cap from the inductor, 5 amps to the inductor from the cap. This inductor over here needs to have a grand total of 7.5 amps. So it's going to get its additional 2.5 amps fed in from there. We get 2.5 amps feeding in from here, 5 amps that is feeding in from here. Gets me to my line total of 7.5 amps inside of that inductor that we have over there. A couple of other things that we still got to go and get to. We got to get to our net vars, and we got to get to our power factor. Power factor is going to be the cosine of our angle, so we're going to go and take a cosine of 22.6, which gets us to a 92.3% power factor. What type of power factor is it? Well, if I take a look, I've got net vars lagging inside of there, so it's going to be a inductive or a lagging power factor that I've got inside of there. And then the last thing that we've got to still pull out of this one here is we need to pull out impedance, and we need to go and pull out our nets out of this one. So we're going to go take this 780 VA, we're going to put it back into our calculator. It's already in XY mode, so 780 angle 22.6 tells me that I've got a grand total of 720 watts. We already have that value, and my net amount of bars is going to be 299.7, or a net of 300. If you take a look at this, you should see 900 bars up, 600 bars down, leaves you with a net of 300. Same as what we just calculated off of this one here. We'll place that in there, 300 bars L as my net. That's what I'm going to go and see from my source. My source is only supplying 300 of those bars. 600 of those bars are being supplied by this 600 bars over here in that back and forth manner that we talked about. Last of all, for impedance, impedance is going to be R is equal to my E over I. So 120 volts divided by 6.5 amps will tell me my total line impedance. 20 divided by 6.5 gets me to a value of 18.46 ohms. 18.46 ohms of impedance that we're going to go and have over here. All right, have we covered everything inside of here? They wanted to know the current in each branch, which we've got that. We've got the line currents. That's the 6.5 amps over here. They wanted to know the total impedance, 18.46. They wanted to know the true power, or the watts that we have. It's going to be 720 watts, our total watts that we have for this one. They wanted to know the magnetizing bars from the coil and from the capacitor, the 900 bars L and the 900 bars C. They wanted to know the net magnetizing bars, that's this 300. They wanted to know the power factor, 92.3%, and the phase angle of 22.6% as well. We've got all of those values. We will move on now to the next one, which is going to be my parallel circuit resonance.